Hello, everyone.
Hey, welcome everybody.
Hey.
Welcome.
Hello.
Hello, everyone.
Hey, we have more and more people joining every week. This is good. Yeah. This is a good. Okay. So I guess we can start. So welcome everybody to the Madara community call number 4. I will share the agenda for the community call. Okay. So basically, first we will start as usual by a backlog review and an update from the different contributors on the different ongoing tasks. Then we will talk a bit more about the Sharingan testnet progress, about the timeline and what needs to be done in order to achieve this goal. Then there will be an introduction to Cairo to MLIR project by LambdaClass. Then there will be a deep dive into the implementation of Starknet called RPC Endpoint, because it will be important as a reference pull request for contributors that are that started to implement some RPC endpoints, like basically how to implement properly a Starknet RPC endpoint on Madara, how to write tests, unit tests, and also integration tests. So Matthias will do a deep dive into this RPC implementation that will be kind of reference implementation for other RPC endpoints. And then Ben will talk about an analysis regarding the Starknet decentralization protocol and the challenges we will face to implement them in a substrate context. Yeah, so let's start by a backlog review and an update by the different contributors. So let's start with the tasks that are in progress. Do we have someone from Finiam that can give an update on this task, the run validate entry point before accepting a transaction in the mempool?
I got some feedback / answers yesterday. I'm just going through it right now. Still haven't take on the work per se. We'll try to do it today. Okay,
good. So regarding the transaction fees, so Lucas is not there, but we are pretty good. We are very close to have the implementation of the transaction fees. So basically, Lucas was able to implement the transaction payment palette and adapt it to use the blockifier to run to know the fees and also to automatically do the payment of the fees, like the withdrawal of the max fees at the beginning of the transaction, and then refund if there is something to refund. The PR is almost done in terms of implementation. It remains only the implementation of tests and some documentation about this feature, but we are very close to have it. Okay, then Starknet goal, I guess no need to go through it now because you will do a deep dive later, Matthias. So same for the experimentation about leader election mechanism, because Ben will do a deep dive about that later. There are other on the pending tasks, by the way. Ben, are you there? Can you give an update on the global state root computation task? If you are there.
I don't think he's here.
Okay, so this one is pretty important. So we need to know if Ben is comfortable implementing it or not, because it's pretty blocking. So we need to have it done as soon as possible. So let's see with him if he's blocked or not. And if yes, probably someone else can implement it. What is the name? Sorry, yeah, Dangush. I don't know. Daniel. Yeah, Daniel, please. Can you give an update about the block header hash computation if you are there?
don't think.
Okay. Okay. So there was a pending question about this task, which was so basically we had the computation of the block header hash inside the block header structure, but the problem was that the hash function that was used was not generic, and this is not what we want, of course. So the idea is to leverage the hash implementation we have in the palette, which can be determined by the runtime, so that it's very easy to switch from a hash function to another one. So for the moment in the runtime, we are using Pedersen hash function, but it's very easy to switch to Poseidon because it is configured through the runtime. So the idea will be to use the hash function from the palette that is defined by the runtime and use it to compute the hash of the block header. So I suggested the simple and pragmatic approach to Daniel, which will be basically to directly compute the hash of the block header in the palette, because the palette already has this system hash trait implementation inherited from the runtime. So this would be the most pragmatic solution. Okay. I guess, yeah. Timothée, can you give an update on that one and the challenges and the discussion we had today about it?
Yeah, sure. So the idea is that the block header should contain the state commitment, which is basically the root hash of Patricia Merkle tree of all the transaction and the change the state went through during the block. And we had a feedback from Starknet explaining that this operation potentially can take a lot of time to compute. Some estimation stated that it could be at most like 1/3 of the block time. And the bigger the block, the more time it takes. So our idea was to execute it asynchronously. And so while you are executing the block n, you also asynchronously, like in parallel, compute the proof of the block n less 1. And at the end of the block n, you put the proof, the root state commitment you had time to compute, and you put it back in the header. So each block will contain the hash of the previous block, but also the state commitment. So this is the idea. It could be better in terms of performances. The problem we face is that basically there is not really easy way for the consensus, the client, to feed some data inside the runtime. So that this will be the idea, like the client compute the state commitment, and at some point it feed it inside the block it is producing. But the way frame is set up, it doesn't offer us like the modularity for this specific thing we want to do. So I had to do it. I have it, it's work, but it's through off-chain workers. And so we have an off-chain worker which will compute stuff and then submit a transaction to the memory pool of the node which is producing the block. And this transaction will be accepted and update the storage. So it works, it feeds the value to the runtime during the block, but it's not as good and as flexible as we would like it to be. The problem is that without actually forking the substrate, some trait of the substrate framework itself, we are not sure we can do this otherwise. So right now we are in this state where we have something which work. We are not utterly happy with it, and we will wait, I believe, for the implementation of the state root commitment, state commitment computation to take decision further after maybe some performances test and stuff like this.
Yes. Yes, basically, yeah. The one of the limitations we have with the off-chain worker implementation is that the off-chain worker first is not guaranteed to be run on each block. This is the case almost every time. I never saw a case where it's not, but it's not guaranteed by the runtime to be run on each block. This is the first thing. And then the second one is that the off-chain worker needs to run in a no STD context, so without the Rust standard library, where on the client, we have access to the standard library, so we will have more flexibility to basically do more crazy stuff and more parallelization, etc. So this is why we will probably investigate another solution than the off-chain worker to have more flexibility and more power. But yeah, okay. Thank you, Timothée. And then we have all the implementation of the different RPC, but they are kind of blocked because we wanted to wait to have an actual reference implementation, and now we have it, and we will see it later. Yes. Okay, do we have Terence or someone from Dojo? I don't think so.
I just wanted to ask Paul Henry if he's here to maybe give an update about the Starknet API PR.
Ah, yeah, good point.
Yeah,
I think he's here.
yeah, I'm here. Yeah, you're very lucky because I was just going to jump on and go pee because I'm gonna pee myself. But the API, the PR about the API OpenRPC from Starknet is going I think pretty well. The documents that are generated are pretty good. They are auto-generated by OpenRPC typings. So it does less Rust typings, or you can do TypeScript typings, so it's pretty cool. It's going pretty well. I've been discussing once with Ariel and once with someone else that I don't know, but they reviewed it. The second review had only like 2 comments that were very minor typos and very small fix. So I guess I'm waiting for now for another review potentially from other people, or just an approval from Ariel or someone else from Starkware, and then I guess it could be merged. But the types that it generates seem pretty correct, and I've managed to fix, like, I think all the errors, what's like all the like the scrambled types, and also there were like some results that had like everything optional, so I was also able to fix that. So now it's the types that are generated from the OpenRPC seem correct. So
nice. This is very cool. Yeah, this is very cool. Okay, thank you very much. So there is no one from Dojo, so we won't have an update about the gaming part of the demo. So the Sharingan testnet, the idea is to basically run a public testnet with Madara, and then deploy an on-chain game using Dojo on this testnet, and do a big demonstration with a multiplayer game at a large scale. So for the testnet, I guess that feature-wise, we are pretty close, I guess. Obviously, we need the implementation of some RPC endpoints, so that the people can deploy easily smart contracts, etc., using actual Starknet tooling, because it's already possible to actually deploy on Madara and interact with Starknet smart contract, but you need to do that through Polka.js API, and the normal way of interacting with the substrate node through extrinsic transactions. But obviously we want full compatibility with existing tooling, and that will be done through the RPC layer. So we need a few endpoints to be implemented before being able to have this demo. Yeah, okay. Hopefully the idea will be to have this demo early May. That will be very cool. First week of May or the second one. hopefully we will be able to do that. Okay, now we can move to an introduction of Cairo to MLIR project by LambdaClass.
Hey guys, Fede's here as well. I'm not sure if you want to talk, Fede, or if I should just go ahead. I guess I'll go ahead. Just to give everyone a bit of background, right? So you've probably read the updates regarding Cairo 1. How one of the major contributions it has is the new Sierra intermediate representation. And the goal, what MLIR wants to do is to take Sierra and compile it down to native code. Right, so that's it in a nutshell. We'll get to the whys afterwards, but first, what is MLIR? If you're not a compiler buff, it may be something you've never heard about, but you've probably have heard about LLVM, right? So LLVM is a compiler backend. It generates, you give it a representation in memory of a program, it translates it into a generic intermediate representation, and then it lowers that into the machine code of whatever, you know, architecture you're targeting. LLVM-IR is a large project. It's mature. It started out as a research. It was adopted by Apple. It then led to Clang. It led to Swift. Rust uses it to generate its backend code. And for that reason, it was chosen for like an initial approach. And it's a great tool. But over the years, what has happened is that many different projects have adopted LLVM-IR and have found it to be a bit too low level, even though it is an abstraction of what a low level intermediate representation is, over an abstraction over the architecture. There are still many problems over which it's very difficult to reason about the program in that state. Specifically, when the people doing machine learning and TensorFlow type calculations, matrix multiplications, they have found that their need to express computation graphs was not very well met by LLVM-IR. So Chris Latner, who was also the founder of the initiator of the LLVM project, started MLIR with that goal of developing something a bit more higher level. So it's called MLIR for a multi-level representation. So MLIR is in production, as you can see, in TensorFlow and a bunch of other projects. There are different compilers that already target it. But basically what it does is it abstracts over IRs. So if you've programmed in assembly, you usually have a mental model of your assembly as like a sequence of instructions. The processor takes each one after another and operates in memory on your values. MLIR is a bit more higher level than that, and what it does is you establish a set of dialects, and a dialect is a set of operations, and an operation eventually maps onto what an instruction would be. So with that higher level in mind, it allows you to do other optimizations. Most of MLIR is in C++. There are some auto-generated bindings to the C API that it has, and that's what we're using in the Sierra to MLIR. So what we do in the project is we take the Sierra representation of a Cairo 1.0 program. We can talk about what that looks like in a bit. And what it does is it translates each segment, each instruction in the Sierra into an equivalent set of instructions in MLIR. And then it just hands it off to the backend and says, okay, with this, can you please optimize it and generate some native code and then run it? So if you haven't taken a look at some of the articles posted by both the Starknet and Nethermind, Sierra as an intermediate representation it's also a linear representation. It's in the sense that it's a sequence. The Sierra program is basically a vector of libfuncts. And the goal is that when you compile your Cairo to Sierra, you have some guarantees built into that transformation, right? So there are some things that you can depend on already. You can depend on that you won't have infinite loops, that your program is sound, that your assertions will not fail, your dereferences cannot fail. It has a type system that ensures all that. That's the new thing in Cairo. So with those guarantees, we can also transport them to the native code that is being generated, right? one of the things, why would we do this? Why do we want to take the Sierra IR and translate it into native? Well, the obvious reason would be to make it go faster, right? Because if you take the Sierra is then translated to Chasm, the Cairo assembly, and then Chasm is interpreted by the Cairo VM. That interpretation is done so that you can generate the trace for which you can give to the prover, and also to get the results of your program. If you take away the necessity of generating the trace, that's a lot more work that you don't have to do, right? Exactly as they're saying in the chat. The VM is for generating the traces, and MLIR is just to get the results, and also to compute the gas. So the idea is that a sequencer can use this representation to take incoming transactions, execute the Cairo programs associated to those transactions, and then quickly and with very low computational cost, determine whether the transaction is valid, what the result is, and whether the gas computation is correct, whether it has to be accepted or not, and so on.
Yes, exactly. So
it's still very early days. Sorry.
Yeah, just to give some context, and then I will let you continue. Sorry,
Sure.
Sorry to interrupt you. Yeah, basically, the idea, like, this is the current architecture for Starknet, which is centralized, but it will be the same in a decentralized context. So we have the sequencer that validates transaction, run the Cairo VM, which is the Cairo RS virtual machine by LambdaClass, then produce block and update the state, and then asynchronously the prover generate the proofs and settle the proofs on the layer one. So what we want with this Cairo to MLIR project is to remove the need of having the Cairo VM here in the sequencer, being able to run extremely fast Cairo program with their representation in MLIR to run in native speed and remove the overhead of the VM and remove the need of doing unnecessary operation when you don't have to prove. But then obviously the prover needs the Cairo VM still, because it needs to generate the execution trace and so on. Yeah, please continue, Iñaki, sorry.
No, I was just wrapping up and saying it's still early days. We've gone through several prototypes. We can take small Cairo programs, translate them from their Sierra representation, and then run them. Initial benchmarks are very, very encouraging. Like the difference in execution time is in the order of 3 orders of magnitude. So if it would take, for example, 80 milliseconds to run a Cairo program through the VM, it takes something like 10 microseconds to do the same. It's a large difference. Take into account that it's, one, because you're removing the interpretation overhead, and 2, it's also mostly because you're doing a lot less work as well.
Yeah,
it's very difficult to compare apples to apples in this context.
Yeah, sure, sure.
So the main concerns right now with the project is to get to a point where we can run all Cairo programs to begin with. Second, to make sure that the semantics are correct, like if you generate the code natively, then it'll do the same, and the results are correct.
Yeah.
So, and then finally, once we get to that stage, we're going to start looking at well, how could this be integrated into other projects?
Yeah. Okay, exactly. So yeah, there is an interesting question about the asymmetry once we have that, because the sequencer will run extremely fast, but the prover will still need to use a Cairo VM. But the thing is that the proving is done asynchronously, and it is massively parallelizable. So this is a big difference. This is why it works actually. You can run extremely fast on the sequencer, and you don't care about the proving because it can be done in a massively parallelized way. You just have to spin up a bunch of machines and do everything in parallel, and using recursion of the proofs, it works. This is why this model can work. Yeah.
Exactly.
Yeah. Okay. Thanks, Iñaki, for the introduction. So this is very promising, and as you said, the first benchmark are very impressive and very promising. So we can't wait to integrate this into Madara to have a blazing fast sequencer. Yeah. Also, maybe
I'm working on doing some like a post, kind of like elaborating everything I said. Well, I'll let you guys know when it's published, and also documentation. You know, the idea is that this should be pretty simple to just plug into whatever.
Yeah. Okay. Okay. Nice. By the way, maybe also Iñaki, you can discuss a bit also about Starknet in Rust, because basically currently we are using the blockifier, which is the component that executes transaction, compute the state diff, etc. But we are considering eventually moving to Starknet in Rust, or maybe have the possibility to have them both and switch easily through the runtime configuration. One important criteria will be performance. Again, this will be the #1 criteria to choose the execution engine. So we are started to discuss with LambdaClass about what would be needed for us in order to switch to Starknet in Rust. But yeah, if you can give a quick update on that front, Iñaki, that will be awesome.
Exactly. So the Starknet and Rust team is currently focused on getting up to par with the 0.11 updates from Starknet, so that it has the same functionality. And included in that is some refactors from the needs that we've received. One of them, for example, is to have like a pluggable storage. So I think that one is one of the main ones. There's also some work that's going to be done to make the compiler actually pluggable as well, so that you can choose that. But for now, I think the pluggable storage is the main one. I think Bona is here. He can also mention if there's anything else that's being worked on at the moment, but I think it's in the pipeline.
Yeah, yes. We want to make a pass through the code and see what we can improve to make it easily pluggable into Madara. Make as easy as possible to replace the other cargo feature and replace, say, okay, execute it with Starknet in Rust or with Blockifier, etc.
Yeah, exactly. Yeah.
There are also some things I think. So there's a Starknet API, right? And I think we're working on getting also to use that as closely as possible and with the latest version, so that it should be more pluggable. But I think some work is falling off from that end.
Yeah. Okay. Awesome. Very cool. So before jumping to the deep dive of the RPC implementation, we have Terence that joined. Maybe Terence, if you can give an update on the Dojo side for the gaming demonstration for the public testnet.
Sure, definitely. Hey everyone. So on the testnet itself, we've had it hosted for a while now, but not much progress there. I think we're currently blocked just on, I don't know, I missed the beginning of the call, so I didn't get to learn about like where you guys are with the RPC implementations, but we're kind of blocked there. We continue, the Dojo framework is in pretty good shape, but we continue to be blocked by the inability to like, DevNet is super slow. We don't have a way to do integration tests to test contracts just yet. It seems like Protostar is going to come online soon, or as soon as Madara can support it, we'll use Madara for then start writing some integration tests for the framework. And then as far as the demonstration is concerned, one of the conversations that we had was originally we were thinking of like what game would make sense to demonstrate on top of Madara. And like the OP stack did something called OPCraft, which was like a Minecraft clone where just like the voxel grid of the world was stored on chain, and the mining and the crafting and the ownership of like the real estate was like basically all on chain, which is an interesting demonstration. And I think something we could still potentially leverage if we wanted to. But there's some questions around the resourcing of like who's going to actually push on this. There's another project that we're working on called Roll Your Own, which is like a re-implementation of this like classic game called Drug Wars. That's like an MS-DOS based game and has had a bunch of different versions on calculators and stuff like that, that we've made a lot of progress on and have, like design team and a team writing smart contracts and the front end and stuff like that already. So the tentative plan is to potentially use this to demonstrate Madara if we want to push up the timeline and do it like early May kind of thing. And then, potentially we could do something. I think it would be a great demonstration of like the stack. But it maybe will lack a little bit of the wow factor of like massive transaction throughput. But maybe we can have once we have like an initial demonstration of it, we can find some resourcing to do something that will push it even harder. Like I think once we have like the MLIR stuff, we can really show something crazy.
Yeah, definitely. Awesome. Thank you very much for this update. Okay. So before jumping to the two big buckets, which are the RPC deep dive and the analysis of decentralization protocol, I will just give the opportunity to Sam to discuss a bit about EigenLayer. With Madara, we want to have a very modular sequencer that also can use multiple data availability solution. So that we have Diego from Celestia Labs that did the proposal for Madara to use Celestia, but we will also explore EigenLayer. So Sam, please, can you talk a bit about EigenLayer, about EigenDA, but not only about some interesting concept from EigenLayer?
Yeah, for sure. Thanks for the opportunity. Just wanted to say that I'm not working for EigenLayer. I just like the projects, and I'm having fun trying to find synergies with other great projects. So just to give a high-level overview about EigenLayer, EigenLayer is a mechanism to allow the Ethereum Trust Network to be more flexibly used, and this mechanism is called the restaking. So you have stakers taking Ethereum, and they can also restake to secure additional services. So in reality, what stakers do is that they reuse the same stake they are using for Ethereum to amortize the capital cost of staking, and so they are opting into additional stashing conditions, and so they can get paid for additional return. Currently, there is a testnet of EigenLayer, and the first service built on EigenLayer is EigenDA. So it's a pure data availability service. There is no consensus on EigenDA, just data availability. It's run by Ethereum stakers. So you are inheriting Ethereum alignment and the same decentralized set of Ethereum and the same, depending on how much people restake, the economic security. And the way it would work, so the sequencer, or let's say Madara, takes the transaction data, split the data using n-ratio codes and KZG polynomial commitments, and post the data to EigenDA. And so EigenDA nodes are just downloading and storing a small portion of the data. So this make it way more scalable. Just to give some numbers, Ethereum after proto-length sharding, the data rate of Ethereum after EIP 544, it's 83 kilobytes per second. So it's great, but the view of EigenLayer is way more bullish on crypto and not only a financial service. The whole digital economy is supposed to run on crypto. And when you think about things like games and social, we need more throughput. And currently, EigenDA testnet is having around 10 megabytes per second for 0.3 node boundary. So it's a lightweight operation for the nodes participating in EigenDA. And there are different possibilities for EigenDA. It's a very customizable services. And for the moment, it's on testnet and it's working. And yeah, I think that's all. If there are any questions, I'm happy to reply if I can. And thanks again for the opportunity.
Thank you very much, Sam. Okay, then we can jump on the RPC deep dive by Matthias. Yeah, please go ahead, Matthias.
Sure. All right. So because we have a lot of issues regarding implementing all the RPC endpoints, and I see that there are a lot of people blocked because there isn't the transaction transactions are not part of the block body, but that will come soon. But let's look at how are you supposed to go through implementing a new RPC endpoint, trying to make this as clear as possible so that everyone can go fast and not forget anything, especially we'll talk about testing. Can you see my screen right? Okay, perfect. Yeah, so first of all, thanks to, I don't remember who started to write it, but there is an RPC contribution document that goes through first how to build Madara, a quick intro about the architecture. I won't go through this right now. And then, so I've added a lot of things in there, but it had already like a bit of great content. And I will take the example of Starknet call endpoint and kind of go through this to make sure there isn't any missing step in that document. And then you just need to follow it, and it should be pretty straightforward. So the first thing, as we saw, as Timothy presented last time, is this file. So the RPC core source lib file. So there you have all the endpoints definition. So for now, we have block number, block hash end number, get block transaction count, and then call. So if you want to add yours, you just add a new one here. You put your method name. Note that when you will want to call it, you will have to put Starknet underscore in front of it. And then you put your different parameters. So if there is a new parameter, you need to define it. Like for instance, here we have function call, which I've defined here as a struct. When you want to do a call, you need the contract address, the entry point, and the call data. All right, and then you have the block ID, and it returns a RPC result. So that's the first step. Once you've added it here, that's just the beginning. Now you need to go to the RPC module here, right there. And then, so you just follow again. So here in this module, there are all the implementations of the function we've just defined in the RPC core module. So that's where pretty much the whole logic will happen. We can see the logic for get block transaction count, for instance, right there, and so here's the logic for the call endpoint. So there will be a few interesting things. The first one is whether you need or not the substrate block. So just a quick reminder, as we saw last time, we have this infrastructure where every substrate block is mapped to a Starknet block in a one-to-one relationship. And so you can just use this code snippet in order to match the block ID, which is this block ID is like, how do you fetch the block from the RPC? So it could be like the block hash, the block number, or latest or pending block tag. And with this code snippet, we just fetch the substrate block. All right. So when you want to add your RPC endpoint, you just define your function with the same signature as you define the RPC core module. And then there's this important thing, is the runtime API. So if you want to interact with the runtime, meaning calling some functions which are in the Starknet palette or another palette, you will need to access the runtime API, which is you can just fetch from the client object. And then we will see that we will need to actually implement, add the function signature to the runtime API. So for instance, for the call endpoint, I basically created, so let me get it here in the Starknet palette. I needed to create a call function because that wasn't implemented there. And you will probably, in a few different cases, need to add some functions there as well. So there it is, call. So that will be an internal function, right? We're not talking about external function. So here is it, the Starknet palette internal function. We have current block hash, we have parent block hash, block timestamp, transaction count. And then I needed to add this call contract function. So it's part of an internal function of the runtime. So that's why I need to fetch that runtime API. It takes as parameter the same thing, address, selector, and call data. And we do a bunch of things here. Essentially, it's pretty much the same as executing a transaction, except that we're directly creating a call entry point and executing it so that there is no real transaction that's being done, no need of signature or anything. It's just executing the entry point. And then we get the return data back from the call info object, and we return it. Here it's important to note that compared to block timestamp that always return a result, here there can be some errors that you will need to handle in your RPC implementation. So here we can see that we call the function from the runtime API, and we need to handle these errors. So you have all the errors already defined here in the RPC API error enum. Just pick the one that makes the most sense in your case. That's something that I guess we have to define a bit better. Because there are some errors that are not part of the RPC spec. Sometime it is, sometime it's not clear like which error you should throw. So that's yeah, I guess that's something we have to work on to define that a bit better. Like here we have some error in the parameters of the RPC. I chose to return the internal server error, but probably there are better ways of doing it. But still, but the most important is that you handle all the errors, right? You don't want to use unwraps anywhere there. All right. Okay, so let's go back to the guide. Yeah, but so pretty much that's pretty much everything here. Then you need to implement the runtime API, because if you want to have your method here, the call method available, you need to add it through the runtime API. Right, so RPC. So runtime API, let me get where it is. Okay, so it's in the runtime API file, which is in the Starknet palette. You have here, we have only current block hash, current block, and call. But of course, there will be many more pretty soon. And here, it's important to know that it's in the runtime, it's no STD environment. You cannot use the string parameters and things like that. You should be using the wrapper types. You will see often that we have like wrapper types and native types. These are just to comply with the substrate environment. And there are wrappers around the Starknet API crate. And so you just put the function signature here, and then you'll be able to access it in your RPC definition here. All right. I guess that's pretty much it for at least how to implement the endpoint, and we'll go through the test. But just checking.
You have a missing part, which is in the runtime. You define the runtime API and say which function to call. So this is in the definition of the runtime. So the lib.rf in the runtime.
That's what I just went through. I mean, adding this here.
No. Here, this is on the palette, right? No.
Yep. Yes.
Okay, but you also have something in the runtime. Yeah.
Yeah, you have to implement the runtime API.
Yeah, exactly.
Yeah. Yeah, sorry. It's written in the documentation. I wanted to do it by heart. But yes, let's go back to the document. It's very handy that everything is written here. So we added the function signature here, your new function, and then we have to implement it in the runtime. All right, so that you can just go to search for runtime API here. And that's where you can actually interact with the palette. So right now we only have the Starknet palette, but you could technically interact with any palette you want, and you call the method from the palette, the internal method. So call contract with the different parameters. So pretty straightforward. It's a bit just follow the document and you should be good. There are a lot of back and forth between injecting things between the runtime and the client. It's a bit tricky at first, but yeah, just follow the steps and you should be good. Okay, now you've done all that. First, are there any questions maybe?
Yes, go ahead,
Yeah.
Pierre.
Yes, sorry, I have a question. So basically when the RPC call arrived in the client, so you show the interaction between the client and the runtime. So, but also Adele talked about the synchronization of the database on the client side. So just to be sure and clarify my understanding, it means every transaction, every RPC call that needs to interact with transactions blocks has to go to the runtime because the runtime contains all the logic to access this data, or there is a way that the client can be aware and directly access the storage. And from my understanding,
there is a way to do it, but it's less like we actually do it for the. So there was a trick Timothée went through last time. You can if you know how the storage layout looks like, you can directly go and take that data from your database, but it's less error prone in some cases. You won't always know where it is in your database, but it could be a very performance improvement. And you have this fallback mechanism where if it doesn't find it in the database, it will execute it through the runtime. Is that right, Timothée? Just
Yeah, exactly. It's in a section which is called override. And the idea is that if you have some insight about like the way your storage is set up, you can directly index the storage without running the runtime itself, because it has a cost to runtime, to spin up the runtime and query it. So if what you want is just to read a value that is somewhere in the storage, you can go through it, and with the override, you will be able to do this directly. And there is this fallback mechanism, like if you don't find what you are looking for, you will instead call the runtime with the method. So this is a really efficient and safe way to go. The difference is that when you use it, you are really just reading something from the storage, while when you do a runtime API call, there can be some computation also, which is made by the runtime. Like as long as it doesn't edit the storage itself, it's read-only, you can add computation in it. And so
it depends on the RPC endpoint you're working on.
Okay. So perhaps a first way to approach it is in an easy way going to the runtime, just to be sure we follow the logic, but really if performance is a matter, we can just try to make the former, right?
You can just look at here, there's an example.
Try to implement like the override for this specific read. There is other implemented, so you will be able to mimic what's already there. And then you can use this, it will deliver better performances.
Thank you.
Yep. Right. Any other question before we go through the test? I saw that there was someone asking for we create a function, suggesting we create a function to instead of having to copy paste this whole code snippet every time. Definitely we'll do that in this PR, so it's you will have it. Okay, so now that you've implemented your endpoint, let's write some tests to ensure everything is working correctly. So test, that's something we haven't gone through any time yet, so I will go through it. Integration tests are written in TypeScript, actually, because we want to test the compatibility with Starknet JS tooling. That's pretty cool. We want to make sure Starknet JS just works in a seamless way to interact with our Madara blockchain. So tests are written in TypeScript using Mocha and Chai for those familiar with that testing framework. So you have two folders. This one is the TypeScript API. You don't really have to, usually you won't have to edit anything in here. The TypeScript API is just a package we deploy to NPM that defines like the TypeScript typings for our blockchain. It's like a wrapper around Polkadot.js API, and will just make your life easier when you're writing those tests. And then here is the test suite of Starknet RPC. So very simple. We get the provider RPC before all test, which so there is this describe dev Madara that will basically run a node in the background while you're running your test, and give you some context about some just setup. So it's set up on a random available port and gets you the ideas that we will probably do that in the context as well. That could be an interesting task to work on. And yeah, then you can easily test your endpoints using the Starknet JS RPC provider. So here, for instance, get block hash, just simply call it. Then you can write some test. Like for instance, here for get block number, we get it. Then we have this very cool method, jump blocks, that we needed to modify a lot of things in the runtime in order to be able to do this. But when you're running this these tests, the node is actually not producing any block by itself. You have to, you can tell the in the test, you can tell it create a new block, create 10 new blocks. It's very granular, and you can create blocks with whatever you want in, jump 10 blocks. So for instance, here we test that the block number is increasing correctly. Yeah, and then pretty much classic test, like for call. Yeah, we just specify the contract address, the entry point, and then the call data. So that's yeah, that's pretty much it. Let's see how to run these tests. So to run this test, you simply go to the test folder. So when you're in root, you go to the test folder. Maybe I can make that bigger. Okay. Okay, so you go to the test folder. Then you will need to install all the dependencies. You just do npm install. And then, so then you can do npm run test sec. So that will run all the tests sequentially, or just npm run test to run them in parallel. But I suggest you easier to debug to run them sequentially. All right, it's in action. All right, so all the tests are passing. It's pretty fast. And it's working. So the node is running in the background. Sometime when you will be working on your own test, you want to see what's happening, especially if you have errors. You want to be able to see those errors. How can you do that? You just specify Madara log, and then so you have different log levels in Substrate, like info, error, debug, depending on your situation. You just specify it before running the test, and then you do the same command, and now we will see the node. Yeah, so we see the node running here, manual seal, and we see the transaction going through. You can see that we've jumped 10 blocks with the jump blocks util command, and then yeah, you can, if there are errors, you will see them here, and it's way more handy to debug. Okay. Guess that's pretty much it. Note that for now, we're just testing for one node. We're not testing against like a network of nodes. And as Timothy mentioned at some point, there are errors that can only happen when we have multiple nodes. And so we will be we'll be able to write tests with a network of nodes in the exactly same fashion, thanks to a very cool library called ZombieNet, developed by the Parity team. So, but that's for another time. All right, I see that there are a lot of messages in the chat.
Yeah, basically the question, most of the questions are about the different guarantees you have when you run some computation in the runtime versus on the client side, and the different possibilities. So maybe Timothy, you want to give an overview about the main differences?
Yeah, so with what we are doing, we have like 3 levels of code execution. We have the client, which will execute code, do the RPC things, all those things. It will also reach a consensus. So they are going to check if the blocks are valid or not. We have the runtime, which is in charge of producing the new block. And we can be sure that everything which is in the runtime will be executed on every node of the network. And then inside the runtime, we have like the Cairo code, which is the code which is provable. So we have those 3 layers of security on the code. So what I mentioned is on the thing we were working those days, which is like the state commitment. We don't want it to be executed in the runtime because it takes a lot of time. So we want it to be computed by each node outside of the runtime, but we still want them to reach consensus over which is the correct value. So in order for a block to be accepted, it will have to contain like this correct value. So we had to modify the part of the client which is accepting or refusing new blocks. And by adding extra checks, we can make sure that every node in the network agree in the same way on what is a valid block without having it computed in the runtime itself.
Yes, and basically everything in the runtime is sequential, where on the client you can do parallel computation, and also you have access to the standard library. So it's easier to do crazy stuff on the client side. The client, your client part, you cannot update it using WASM runtime upgrades. Yes, exactly. Yeah, you can only upgrade the runtime. Yeah, it depends on the use case. Exactly, it depends on the trade-off for each use case. Exactly. Yeah.
Just adding a last thing, every time you're doing changes to your Rust code to work on RPC, make sure to build it again. Yeah, you need to build it again before running the integration test. You can, so there is binary, you have a binary path here in the constants file. You can specify where your binary is. So depending if you're building in a release mode or debug mode, you can just put debug instead of release here, or specify the environment variable. And you can finally test in local just by using Postman or a curl command to test the endpoint. But it's very important that we make sure we're compatible with Starknet JS.
Yes, definitely. The idea would be to have Madara as a plug-and-play solution to the existing architecture. Yeah. Okay, thank you very much, Matthias. This is very helpful for contributors that will work on RPC. So when with that plus when we add the block body in the storage, I think everything will be there for the implementation of almost all RPC endpoints, at least all those needed for the demo. There might be some few that will be trickier, but yeah.
Now that we have this document, I think everyone will be able to, we can have this
Yeah.
in 1 week, all the endpoints, and
Yeah.
so that
I think so. Yeah.
pretty much everyone is working on at least 1 or 2 endpoints, so that's a great thing to everyone for
Yeah, that can be very fast. Yeah, definitely. Okay, then the last item on the agenda is Ben talking about different challenges regarding the future implementation of the decentralization protocol of Starknet. Just to give a quick overview about the current proposal. Basically, you can think it about, there are basically 4 main functions. First one is the leader election, then the consensus, then the proof production, and then the state update. So the leader election is how you select the node that will produce the block. The consensus is how you come to consensus. Then there is a proof production, which is the generation of the proofs, and then the state update is how you settle on another layer. Yeah. So please go ahead, Ben, and explain us your analysis.
Yep, sounds good. What do you want to do about time? Because it looks like we're at the end.
15, 20 minutes. Yeah.
Okay. All right, can you guys see my screen there?
Yes.
Okay, so I was going to put together a fancy slide, but ran out of time. So the left here is going to be the spike details. So we have a spike issue here just for going over what Abdel just mentioned. So on the main Starknet forum, Ilya has put together a series of posts basically going over what Abdel just mentioned. So an introduction to the entire protocol, a candidate for leader election, consensus, proofs in the protocol, checkpoints for fast finality, the buffer problem, and then chained proof protocols and braiding. So one of the scopes of this spike is basically, are we going to be able to use Madara for a canonical L2 sequencer, or is it not going to be feasible for some of the reasons that we've talked about today, which is, what are the limitations we're going to run into with the communication from the client to the runtime? Because certain things in consensus can't be done with an off-chain worker. So this is some of my findings that I'll go over here. The architecture for Substrate out of the box is splits consensus into 2 mechanisms. One for block authoring, which does the block proposing for nodes, creating new blocks, and then the second is block finalization. So this is where you get finality in Substrate. There's a couple different palettes that are implemented here, and the usual node template comes with something like an arrangement of Aura and Grandpa. So briefly, I'm going to talk about what that is, and this is what we use today. We use Aura and Grandpa. Aura for block authoring and Grandpa for deterministic finality. So Aura is an authority-based round-robin scheduling. It just is rotating through the list of authorities. So it has some vector of authorities that it's going through, and it rotates through that list. And it says, for each one of these trusted authorities, we'll round robin and give them the opportunity to propose a block, and that's what we use today. Majority of online authorities are assumed to be honest, and it's usually used in tandem with Grandpa, which we do. A alternative reference implementation to this is BABE. It's called Blind. The acronym is Blind Assignment of Blockchain Extension Slot-Based Scheduling. So it's a slot-based scheduling, and basically instead of doing something based on a round robin, it's going to use some randomness and assign to the authorities who's going to be the block author, and the winning authority can select the chain and submit a new block. Okay. So these are the things that kind of come out of the box with Substrate. I'll get into what parts of Ilya's decentralization posts we'll be implementing in this spike. But before I do that, I want to talk about the alternatives, the same alternatives for fast finality and finality gadgets. So the one you've probably heard of is Ghost, greediest, heaviest observed subtree. This, you'll probably know this from LMD Ghost on Ethereum. The Substrate docs have some pretty good diagrams for it. So Ghost here is on the bottom. Basically, it's going to go based on whichever subtree has been built on the most. So in this case, it's this subtree. The the default fast finality for Substrate, and the one we use is Grandpa, deterministic finality mechanism for blockchains. It's basically just saying the longest chain rule is equals to the best chain. The best chain is the longest chain. So that's demonstrated up here above. This is the longest chain. So this is the one that Grandpa would come to consensus and finality around. In Ilya's series of posts, he does go through a finality mechanism. So that's, if you want to check it out, it's here. Checkpoints for fast finality. These are fairly verbose, so I do recommend everyone goes and reads them. But you know, as far as the spike goes, it is pretty dense reading material. So one of the scopes of this spike is basically going to be, how do we implement candidate for leader election, the post 2 here, and checkpoints for fast finality 5 here. So I'm proposing that we go through this and separating them a similar way that Substrate does. We're gonna have a palette called Bookie. This is from his post. So similar to some of these slot-based scheduling for leader elections that we've seen here, it's an epoch-based stake-weighted scheduling. An epoch is 5 minutes made up of slots of 15 seconds with a public lottery based on L1 timestamps. So this is the asynchrony that we've talked about through some of these other problems, where basically, you know, we're coming to consensus about an L2 based on facts on L1. So we're going to have some misalignment of you know, the global state of time here, which is going to be an interesting thing to solve, but I think we might have a path to it. So leader election is based around some randomness and stake distribution that can also be calculated off chain. And then the state update of the L1 core contracts ensures via proof that L2 block authorships follows a schedule. For the sake of time, I'm not going to go over hot stuff. There is a issue open for this for someone to basically implement this in a palette, and then we can look into using it. I'm also, for the sake of time, not going to go into quorum. If you want some more information about that, you can look at Ilya's post. It's post 5 here. But I'm just going to dig into a little bit on what's been done and what needs to be done. Zoom is cannibalizing my screen here. Okay, so that's hot stuff. Abdel has a link to the paper in that issue. These are the protocols, blah, 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 protocols. Okay, so what needs to be done? One of the things that needs to be done is identify the API and the interface between getting this consensus data from Ethereum L1 into, you know, not only the runtime, but the nodes. So we'll talk about that a little bit, but Polkadot has this concept of cross consensus message format, XCM. The cross consensus message format is basically, you know, it's what a lot of the relay chains and parachains use to come to consensus and get randomness from the parachains. But I think it says it in here, you know, you can use it. We can basically use it for standalone consensus mechanisms as well. It's a fairly new protocol, so I would be interested. I know there's at least 2, you know, really hardcore Substrate devs on the call. I'd be interested to hear feedback if you guys have used this before. It looks like the best path forward. But basically, we'd be taking this path, so solo chain up through one of these transport protocols into the palettes to come to consensus via this message format. This is the thing that is still kind of a black box implementation. So I'm going to go over some of the other stuff that's been done. Okay, so there's this repo called Zon. I checked with Ilya, and even though this is kind of the best candidate for the decentralization protocol of Starknet, there's not currently an implementation either internally or externally that I've been able to find of any of these contracts in Solidity. So this is kind of the first attempt at what these might look like. So this is a bootstrap project with Foundry, and I'll go through a little bit how to interact with it and how it's set up. Okay, There's another issue in our backlog that goes over implementing the Stark token. It looks like that issue is specifically to have the Stark token just deployed as an ERC on Starknet. But one thing that whoever's implementing that ticket, if you do want to take a look at, I've added the Solidity code as a Git submodule here for the Starknet token. And basically, if you guys are familiar with Foundry, it's just this kind of Solidity testing suite. It also implements something like Ganache, so it has this concept of Anvil, and you can have this local chain operated with your deployments. So basically, you can deploy the Starknet token. Yep. Was there a question?
No, I don't think so. Yeah.
Okay, cool. And then also the core contracts here. So the Starknet core contracts, we're basically going to be deploying these as kind of tooling. I'm not currently using either of these in this exploration. This is just to kind of come to consensus around Ilya's first post around leader election. I'm not going to go back into it. Okay. So there's the bookie.sol. So bookie.sol is this concept of we have to have some amount of stakers on L1 that we know they're going to be, they're going to have an EOA, they're going to have some stake in the Stark token, and so that we can slash them if they're making a bad proposal, if they've missed their slot, all these types of things. We also need to have some schedules. So we have the epoch builder here, and some of these things from the post. So an epoch is going to be 5 minutes. A slot is 15 seconds. So we have a certain amount of slots and a certain amount of seconds in an epoch. And then we basically build the epoch and assign some randomness. So as of the merge, we have this opcode called prev randao. So randao is a VDF, or not a VDF, a VRF that the beacon chain uses to bootstrap its randomness. We can basically piggyback off the same thing. And out of the set of stakers, we can basically assign random leaders to each one of these slots. So we come to a schedule that makes up an epoch that we can then query. So let's look at, here's some testing around it. But the more interesting thing is to deploy it on Anvil. So there's a script here. I'll run it first. So that starts Anvil with some pre-deployed contracts. And then what it's going to do is it's going to deploy the core contracts of Starknet. It's going to deploy the Starknet token. And then it's also going to deploy the bookie contract, all using a pre-deployed account. After it does that, we build an epoch, and we build an epoch every 100 seconds. So this gives us the ability to have this scheduling, this leader election scheduling that has been defined in Ilya's post. That's basically where I'm at right now. So the next steps here, and again, I would love to hear feedback from some of the substrate devs, is basically to hook this into the cross communication messaging protocol here. Yeah, any questions, or do any of the substrate devs have experience with XCM?
Timothy, here. I know it's one of the part of substrate I never touched. From what my understanding of it, it's more like more than a protocol. It's more like a way of representing the message and the instruction, and it make it like chain agnostic. So I strongly believe we can use it for this use case, but we will have to learn more about it, because right now I'm not at all fluent with it.
Okay,
Yeah.
and there is Justin on the chat who seemed to have an experience with XCM. Feel free to jump in if you want, or you can talk. Yeah.
I had used XCM a bit for a POC as part of some previous work, and it was implemented on a bridge, and I can just only corroborate what Timothy said. And in that it's more of a format. So XCM doesn't provide any protocol for performing the communication across chains itself. So that's something we would need to implement in some sort of bridge. And I'm sorry if I may have missed any parts about any bridge infrastructure we have. But yeah, there's examples of doing this across a solo chain to pair chain, but I thought there may have also been like a solo substrate chain to solo substrate chain.
Yeah, but basically,
solo
sorry,
is kind of a weird term. I just mean sovereign and not a pair chain. Yeah. Sorry.
If you could find that example as a reference, that would be very helpful.
Yeah, for sure. So I posted an example in the chat. Oh wait, why did that not show up? I'll try to find a proper example. The example I am familiar with though does use Parity's trustless relayer. So I'm not sure if it's a great example because it could imply a fair degree of like custom implementation and work to spin it up. Yeah. But something to investigate for sure.
Okay, interesting. Thank you very much, Ben. This is very promising and awesome. Okay, so the next step will be to have this kind of communication. So basically, if you use XAM, we say that this is a format which can be good because we have Madara that is a candidate for being the L2 sequencer, so with the communication with the L1, but it can also be used as a Starknet app chain that can settle on either Starknet L2 or Ethereum directly. So maybe having a format can be a good thing.
If we end up having many layer 3 chain, it's great. Every layer 3 chain use the same format. It could be like a good thing if it's a way Starknet.
There are subtleties there. Like you could have also a shared sequencer, for instance, to have them all interact in an atomic way. That's the path that Optimism is taking. I guess Arbitrum as well. So yeah, and also there was this thing I mentioned in the chat, the beefy palette. I don't know if anyone is familiar with that, but it's basically a palette that has been incorporated into Substrate that is used to write light client bridges. And it's, so light client bridges, it doesn't, it's not a format like XCM. It's being used in production to bridge between parachains and Ethereum. So that could be interesting to look into.
Okay, very cool. Okay, interesting. Then for the communication with Ethereum, which is actually the goal of this spike, this is very specific to the decentralization proposal for Starknet L2 in communication with L1. So I suggest we try to do that on the client side and use an existing library in Rust like Ethers RS and communicate with Ethereum with that. Yes. Okay.
Do we use off-chain workers here, like we do for the
L1 L2 messages? I guess it depends on the complexity. The more complex, the more I will put it in the client, basically.
Yeah, depends on how complex it is. Do you know, Ben, in terms of,
I don't. That's kind of the next task of the spike, is basically to figure out that interface.
Okay.
I mean, as much as we can avoid off-chain workers, obviously we should.
Yeah, for sure.
Okay.
Justin, yes, exactly. That's the Snow Bridge that is using this light client bridging mechanism using the beefy palette. Yeah, that's
okay.
it works pretty well because you just relies on light clients, both on Ethereum side and on Madara side. Yeah.
Awesome.
Okay, awesome. I guess we can stop there.